Okay, guys, as promised, we won't have too much time to review the grade 11 chemistry in class, and so I thought it might be beneficial to just give you a quick reminder of how to do the calculations. So here we are, and if all goes according to plan, there we go, there's my pen. So here we are, just quickly reviewing the lab calculations we're going to have to do. And I'm not going to go through them in too much detail here. You can always come for more help if you need, but basically just to get you started. And so if you recall, we asked you to get some information in lab, and what I thought we'd start with is actually example 2. And I like example 2 because this one requires you to use all the different skills. And this is where we took aqueous hydrochloric acid, right? And we mixed it with solid sodium hydroxide. So you remember that was the second one you did, where instead of putting 100 mils of water in the calorimetry cup, we put 100 mils of the hydrochloric acid, and then we added roughly a gram of solid sodium hydroxide, and you should have measured the temperature difference. And what you should have taken from that, and we'll just put a little sidebar here, is we should have had a mass of sodium hydroxide to put in. And I'm going to assume for the sake of this that I had 1.1 grams. I'd asked you to get roughly 1, so I'm going to assume that I didn't get 1 exactly. I'll assume that I got 1.1, and there it is. You should also have had a volume of HCl, and it asked you for 100 milliliters. I'm going to say we got 84.2 milliliters, because again, those volumes it's telling you to get are the rough estimates of what you should get to make the lab happen, but this number here needs to be precise. It needs to be what you actually had in your cup when you did it, which presumably you measured with your graduated cylinder, so I'm going to say we measured 84.2 milliliters. The concentration of that hydrochloric acid solution, and I should put AQs on these, so I guess I'll do that. AQ. I don't know if you can really read that, but that's okay. The concentration of that solution was 0.50 molar. So to 2 sig figs, I prepared that one quite carefully. And the last thing you should have had was a temperature initial and a temperature final. So this is all stuff that you should have gotten in the lab on the day. And I'm going to assume that we started at 21 degrees Celsius. We'll call that 21.0. I'm just going to do that again. That didn't go well at all. So give me a second for my eraser to appear. Sorry, it's my first time doing this from home with this particular setup, so I'm sure we'll get better at it. So here we go, 21.0 degrees Celsius, and let's say when all was said and done, it was 22.1 degrees Celsius. I have no idea if those will be representative of your real numbers, but that's what we'll assume it was for the sake of here. So again, all of this information here you had to gather while we were in the lab. This isn't information that you could come up with after the fact. It had to come from in lab. And what I want to go through is how we can find what we need to find for this. And of course, what we're looking for is the delta H naught of this reaction. Actually, not the delta H naught, I shouldn't say, because naught implies conditions that we don't have, because we didn't measure the atmospheric pressure in the room, so we're assuming that, and the temperature wasn't exactly 25 degrees Celsius. So it's not a delta H naught we're looking for, but a delta H. And that will be measured in kilojoules of energy per mole for the reaction. So, first thing we need, of course, is just a balanced chemical equation. And in this case, it's an acid-base reduction, and so you guys can imagine me shouting at you for what you get for this, but we will take aqueous hydrochloric acid, just like that. And we will add to it solid sodium hydroxide. And what will we get? Well, of course, it's an acid-base neutralization, which of course is just a special type of double displacement reaction. You can probably hear my kids stomping away up there. Sorry about that. But what we should end up with is, of course, water and a salt. So we should end up with aqueous sodium chloride and water, which of course is a liquid. And there we go. That doesn't look like an L. That looks like, I don't quite know what it looks like. So we'll get rid of that. Now the nice thing about this equation is it comes pre-balanced. We don't need to add anything to it to make it work balancing wise. I've lost my marker, as is prone to happen from time to time. There's my marker. So, with this chemical reaction, there's my marker again. We'll just do that. Okay. With this chemical reaction, we want to see what the delta H naught, or what the delta H is for 1 mole. Now, where we need to start is using Q equals MC delta T to figure out how much energy was involved in this. Now, Q equals MC delta T. Just like that. Well, in this case, Q equals, the first thing we need is the mass. Now, notably, the mass we're talking about here is going to be the mass of the water. Now, because water clocks in at 1 gram per milliliter in density at the temperatures at which we're working at, if we had 84.2 milliliters of solution, then the overall solution should be 84.2 grams. Right? And we just worry about the water in terms of this. All right? We do not worry about the 1.1 grams of sodium hydroxide that are going into it. So we say 84.2 grams of water, just like that. Now C, of course, comes directly from your textbook. So hey guys, I just need a moment here. Great, sorry about that. I just had to get my kids looked after there for a minute. Okay, so we'll get back to this. So we know that we had 84.2 grams of water in this, and again, we're going to assume that all of the temperature change happens to water. Now we know, of course, that that is in fact an oversimplification. We know that there's the 1.1 grams of sodium hydroxide as well, and that is a source of error in this lab using a simple calorimeter where we haven't included that in, but it ends up being very minute because water tends to absorb quite a bit of energy to change temperature. And we'll talk about that, but not a big deal. So 84.2 grams of water. And C for water, I have to look it up. Believe it or not, I don't memorize these, but it's 4.179 grams, grams, what's wrong with me? 4.179 joules per gram per degree Celsius of temperature change. So if you look, 4.179 joules per gram degree Celsius, and that's multiplied by. All right, and that's a constant. You can find that in your textbook. You can find that in your notes. It's everywhere. And then delta T. Delta T is, of course, the temperature change. In this case, it's the temperature final minus the temperature initial, which we'd see here. All right, so if you wanted to say it here, you could say that delta T is equal to the temperature final minus the temperature initial. All right, and in this case, excuse me, it's equal to 22.1 degrees Celsius minus 21.0 degrees Celsius, and there we would go. Now, that means when we're done, we would calculate Q out, and Q would be 84.2. Oh, I guess I don't need to rewrite it with the delta T calculated. You guys are bright and you can figure that out. So we'll do that calculation now. I'm just putting it into my calculator right now. 84.2 times 4.179 times, and that is 1.1 degrees Celsius. And what we get is 387.1 joules. Right? 387.1 joules. You'll note that I've kept an extra sig fig. I suppose I probably shouldn't have done that. So we'll say it's just 387 joules. Now, that is not joules per mole. That's joules for this whole reaction. So in other words, when we took 1.1 grams of sodium hydroxide and we dropped it in the hydrochloric acid, we got 387 joules of energy out of that equation. Now, what remains to be done is to figure out how many moles reacted. And this brings us back to the concept of the limiting reagent, which should have been the sodium hydroxide. It should be, I think that we had more than enough HCl in 84.2 milliliters to consume all of that sodium hydroxide. But technically, we would have to worry whether it was the sodium hydroxide that all reacted, or whether it was the HCl that all reacted, and there's some sodium hydroxide left in that solution. So we need to really quickly figure out how many moles were involved in this reaction. So to calculate the number of moles of sodium hydroxide that were involved, we would have to do this. We would have to say that we started with 1.1 grams of NaOH. And of course, I'm going to use my favorite thing in the world, which is dimensional analysis. So we're going to multiply this by a fraction. And of course, I don't want my unit to be grams of sodium hydroxide, so I'm going to put that down here. I want my unit to be moles of sodium hydroxide. So I'm going to put that up there, just like that. Now, in 1 mole of sodium hydroxide, how many grams are there? Well, I would have to calculate the molar mass of NaOH. And if you look, I've got a really lovely periodic table here, and you can see that sodium clocks in at 22.99, so 23.0, with the 3 sig figs with which we're working in this whole thing. Oxygen comes in at 16.0 at what we're working at, and hydrogen comes in at 1.01 at the 3 sig figs we're working at. And when that's all said and done, that works out to 40.0 grams per mole. I'm not going to show that on here just to avoid the page becoming too cluttered, but there you go. So 1.1 grams of sodium hydroxide multiplied by 1 mole of sodium hydroxide divided by 40 grams. All right, and when we do that, of course we know grams of sodium hydroxide here will cancel with grams of sodium hydroxide there, and the unit of our answer will therefore be what's left, which is moles of sodium hydroxide. And when we do the calculation, 1.1 divided by 40, which again I'm going to do on my calculator, and by calculator I mean my phone, we get 2.75 times 10 to the negative 2. All right, and I'm just going to write it as a decimal. I hope it fits in there. It probably won't. 0. Yeah, no, I'm going to have to erase because I'm disorganized. 0.0275 moles of NaOH. Now, I can guarantee you that we probably have less than that of the HCl, but we have to check to be sure. We need to make sure that we know what the limiting reagent in this reaction was. So, go back to black here. We're going to quickly go here and figure out how many moles of HCl we had. And in this case, and the reason I picked this as an example, is it's different. We don't have a mass of the HCl. Instead, we have a volume and a concentration. We know that we have 84.2 milliliters of HCl. We're going to multiply that by a fraction. Whoa, that wasn't much of a line, was it?